All right, I'm going to be talking through the correct answers on your take-home assessment. If you have a copy of the test that you turned in, I would suggest that you pause the video and take it out so that you can follow along on your own test. And that way, when you get your graded test back the next time I see you in a few weeks, you'll know exactly how it was graded. Okay, so we're going to start. So part one, you just have to choose one of these to sketch. So I'm going to use 4 different colors because I'm going to show you all 4. You only needed to do 1. Okay, so I'm going to start with tan. Okay, so tangent has some asymptotes, so I'm going to sketch those in first. So the asymptotes occur at 90 and then again at 270. And so on and so on. It says to list all the asymptotes here. So for tangent, my 2 asymptotes were x equals 90 and x equals 270. And my graph of tangent looks something like this. And it's just a sketch, so it does not need to be perfect, but it does need to show that you know where the asymptotes are and that you know that it goes through the points 0 and 180 and 360. And I'm also looking to make sure you know the shape of it, that it increases here and is increasing here and so on. So that's tangent. So if you had chosen tangent, you would be done with this problem and you would get to move on. I'm also going to show you the other 3 just so you have them. All right, cotangent is similar to tangent, but a little bit different. All right, so with cotangent, we are going to see it going through the places where the asymptotes were. So it's going to look something like this. All right, so it looks like this. And something to keep in mind is it has asymptotes where cotangent had zeros, or I'm sorry, where tangent had zeros. So the 3 asymptotes that are in the frame for cotangent are x equals 0, 180, and 270. And again, it looks like this. So again, it doesn't have to be a perfect sketch, but it does need to show me that you know the 3 asymptotes and that you know that it goes through 90 and 270. So that's tan, that's cotan. Again, you only had to do 1 of these. I'm showing you all 4. Let's say you said you wanted to do secant. Secant is equal to 1 over cos. Okay, so I am going to find where 1 is. I see it's right here. I remember that cos hits 0 at 90, so there has to be an asymptote there. So it looks something like this. And I'm going to find my -1. And I'm going to find my, oops, sorry, that's supposed to be at 1. Cool. All right, so 1 over cos, which is secant, has the same asymptotes as tan. Same asymptotes. Okay. And last but not least, let me find a 4th color. I'm going to do dark green. Cosecant is 1 over sine. Sine looks something like this. So I'm going to find 1 at 90. And draw my little U's in, making sure not to hit my asymptotes. And I'm going to, at 270, put my -1. Cool. And cosecant has the same asymptotes as cotangent. 0, 180, 360. All right, that's part 1. So for full credit, you needed to correctly sketch 1 of them, and then you needed to correctly say the asymptotes. Okay, feel free to pause the video if you need to. And then also feel free to follow along. The rubric was included in your packet, so you can see how you're being graded. Cool. All right. Part 2. This is about continuity as well as limits. Okay, so taking a look at this picture. Domain, I see that as I kind of do my little picture frame thing, which I am going to do here with some Post-its. Okay, so that is the lowest part of the graph. And there is no other Post-it because that's an arrow. Okay, so the lowest part of the graph is at 1, and that was an open dot. And then it kept going, kept going. This is domain. The part of the domain gets filled in here. So 4 is still part of the domain. Then here we jump to 8. So 8 is still part of the domain. And it goes all the way to infinity because of the arrow. For range, the lowest value, the lowest Y value in the range is at 1. But both of these are open dots. So that's going to be a soft bracket. And then because of this arrow, it goes all the way to infinity. Okay, now for intervals of continuity, we only are focused on X values when we do intervals of continuity. We start at 1. I'm going to use our definition where we want to see when our pen leaves the page. So we start technically not at 1, right? Because it's an open dot. So we start right after 1. And then I have to lift my pen. So this first interval that I just did is from 1 to 4, and they're both soft brackets because there was open dots. Then I have a dot here. And in that dot is the number 4. And only the number 4. So it's one little piece. Then I continue. I started just after 4. And I'm going all the way to 8, and it's a closed dot. So this third interval is open bracket 4, 8, closed bracket, comma. Then the next place I can put my pen down is just after 8. This is open. No, it says just after 8. And then there's an arrow. So that was a soft bracket 8 all the way to infinity. So there are 4 intervals of continuity there. 1, 2, 3, 4. Cool. And so as a reminder, here's our rubric that was included in our packet. Okay, domain and range reach a point. There's 4 points for intervals of continuity because there was 4 for you to get. And now we're about to do the limit questions, and each one is worth a half point because there's 8 limit questions. And then explaining it is worth 2 points. So here we go. All right, our first limit question says, limit as x approaches 4 from the left. Here's 4. Here's the graph. I'm going from the left, so I'm headed this way. It looks like I'm going to hit 4. Second question. Positive 4 from the right. Here's 4. I'm coming from the right. It looks like I'm going to hit y equals 4. These two numbers agree. When the two limits match, that's the only time that this limit can exist. Since they match, the limit is 4. But the reality is not 4 because the closed dot is here. So the true f of 4 is y equals 2. Again, this is what it looks like it's going to be from the left. This is what it looks like it's going to be from the right. This is what it looks like it's going to be in general because these agree with each other, but this is what it truly is. Okay. 8 from the left. So here's 8. I'm headed towards 8 from the left. It looks like it's going to be this value, which is y equals 4. Headed towards 8 from the right. That's this direction. It looks like it's going to be y equals 1. These two numbers do not agree. Therefore, the regular limit, no left or right, doesn't exist. You also could write does not exist. Cool. The true, oh, typo, that's all right. The truth is that f of 8 has a closed dot at y equals 4. So the truth is that f of 8 is 4. Okay. Then here it says, describe a change you could make to this graph so that there is a point that is continuous, but is not differentiable. State the coordinates and explain. Okay. So in order for it to be continuous but not differential, we chatted in class that this situation can only happen in 3 times. It can happen when the function has a corner or a cusp or some sort of vertical tangent, because in all of these cases here, the tangent line slope would be infinity, which is impossible. So tangent line slope means derivative, so no derivative here. And then here and here, you have these situations where you can draw a million different tangent lines. So since you can't draw a unique tangent line, these would be continuous because you can draw them without lifting your marker, but they're not differentiable because you can't draw one tangent line. You can't figure out the slope of the tangent line. So there's a few answers for this that you could put, and I'll just, check if you had put a correct answer. One of them could have been the idea of moving this up. Again, moving the blue up to meet with the purple to create some sort of cusp. That would be perfectly fine. And in that case, it would have been an x equals 8, 8, 4. Another option would have been to just move this red point into here. So instead of this point being at 4, 2, it could have been at 4, 4. And then I'm sure you might have some other ideas too that could be correct as well. So as long as you put a correct explanation here, you'll be fine. All right, so now we're going to move ahead to part 3. Feel free to pause the video if you need to. Okay, part 3. Okay, given the information, draw a sketch of the graph of f of x. Label asymptotes, coordinates, etc., etc. Okay, so they're giving you this information. This is the given information. So it's saying that as you approach 3 from the left, it's going to look like it's negative infinity. As you approach 3 from the right, it looks like it's going to be infinity. Okay, so let me pause. I'm going to go over my graph. I'm going to choose to put 3 here. I'm going to draw a dotted line in. Okay. As I approach 3 from the left, it's headed towards negative infinity. So I expect there to be some sort of shape like this. I'm not quite sure where I want to put it yet, so that's why I just drew a little thing there so far. 3 from the right approaches infinity. So that's going to be some sort of shape like this. Okay, so I'll keep that in mind. I'm going to come back to these two. X approaches negative infinity. That's this direction. And it says it's going to look like it's 3. So that means it's flattening out at f of x equals 3, also known as y equals 3. And as I head this way, it says limit of x approaches infinity is 3. So, okay, so now I have the information that I need. That means that there's an asymptote at y equals 3. So now I'm almost certain that my graph is going to look something like this. But in order to know exactly where to put it, I just want to look here. It says that the limit as x approaches 0, which is along here, of f of x, looks like it's going to be 0. So there's probably a point 0, 0. And I know that it's going to be coming from the left and right because they have to agree if this is true. However, before I put a closed dot, I see here f of 0 doesn't exist. So this must be a hole. Okay, so I'm going to draw a hole. And I know holes have to be on the curve. And so that means that now I can fill in the curve because I already knew it was this kind of shape. Ta-da. Cool. And it could have been this or this. We never know until we try a point. Okay, that's part 3. So let's check our rubric. Part 3, accurate hole coordinates, 0, 0. Accurate vertical asymptote. Oh, I didn't label. Oh, I would have got points off. Let me label. So this asymptote here is x equals 3. And this asymptote here is y equals 3. Okay. So we have our asymptotes accurately, and then we have an accurate sketch. All right, right. Next. Part 4. Okay. All right, so we're going to show a bunch of work. We can use algebra or limits. We've learned both ways. And we're going to have to find any asymptotes or wholes. And if there's an oblique asymptote, we have to use synthetic division, and we can use extra paper if we need to. Okay, here we go. So first I'm going to see if there's any factoring. Looks like there probably is. Cool. That's factored. Can double check our work. X squared minus 1x minus 3x is minus 4x. Okay, cool. Perfect. So we can see that this cancels. So the second we see cancellation, we know that there is a whole. X, so that's our whole, x minus 3. So x minus 3 cannot equal 0. Therefore, x cannot equal 3. Then we take the canceled version, which is 2 over x minus 1. Put the 3 in. X cannot be 3. So when you plug 3 in, you'll get an answer that cannot be. 2 over 3 minus 1. 3 minus 1 is 2. So that's 2 over 2. So that's 1. So the whole is at 3, 1. Cool. Again, wholes occur when you cancel a restriction. We know x cannot be 3. We know x cannot be 1. Because this canceled, it's a whole. Okay. All right. So now we want to find some more asymptotes. So we know that, I'm going to take this restriction. We know x minus 1 cannot equal 0. Therefore, x cannot equal 1. So that's a restriction. And our simplified graph is 2 over x minus 1. So we could write an explanation about a rule where the degree at the bottom is smaller than the top. So therefore, we know it's horizontal. We could write that explanation in words. We also could do this. Plug in as it reaches infinity, as well as negative infinity, and see what happens. And you could have done this for the original or this. I'm going to pick the easier one. So for this, we have 2 over infinity minus 1. Infinity minus 1 is just infinity. Anything divided by infinity is 0. Here, 2 over negative infinity minus 1. Again, that is infinitesimal compared to infinity. So this is 2 over negative infinity. Anything divided by infinity is 0. Ta-da, these match. Therefore, there is a horizontal asymptote at y equals 0. So here's y equals 0. Here's x equal 1. Horizontal asymptote, y equals 0. Vertical asymptote, x equals 1. There is not an oblique asymptote. I'm not going to check that off. It's not there. Okay, cool. I'm almost done. Let me just remind myself where my whole was. It was at 3, 1. So that's all the way over here. The whole has to be part of the graph. So I know that it's this shape. Cool. This is done. This is full credit. If you wanted to be extra, you could plug in 0. And that would show you that 2 over negative 1. This is 0, negative 2. You don't have to do that. The point is to make sure that you have the asymptotes correct, the whole correct, and the shape correct. So going to our rubric for part 4, accurate whole, accurate vertical, accurate horizontal. You did the work and you drew an accurate sketch. Cool. All right. Feel free to pause the video if you need to. All right. Part 5. Okay. Same idea, but it looks a little bit harder. Okay. So let's try this. This top is not going to factor. And we can kind of tell that because if we look at the 2, right, the only factors of 2 are 1 and 2. And then if you're thinking you're going to put 2 cents of parentheses, 1 plus 2 is 3. There's no way we can reformat the factors of 2 to get 5. So this is not factorable. So that's key because that means we're going to have to do synthetic division. Okay, so focusing only on the leading term, what can I times x by to get x squared? X. So x times x is x squared. X times 2 is 2x. Subtract. These cancel. 5x minus 2x is 3x. Okay, what can I times x by to get 3x? That would be 3. 3 times x gives me 3x. Bring down that plus 2. 3 times 2 gives me 6. Subtract. Cancels. 2 minus 6 is -4. Okay, so there is a remainder, which means it's not a factor of this. Great, so it's not a whole. So this is an oblique asymptote. Y equals x plus 3. And you can scroll down and you can check off oblique. Y equals x plus 3. Okay, and we'll come back to the graph in a second. So far we have our oblique asymptote, which we knew was a thing because none of this canceled. And the degree of the top is bigger than the degree of the bottom. One thing we didn't do yet is take the bottom and set up our restriction. X cannot be -2. So that is a vertical asymptote. So we're going to scroll on down. Vertical asymptote at x equals -2. And while I'm here, let me draw in my vertical asymptote. Okay, now it's said to show any asymptotes or holes. I have an oblique I showed, I have a vertical I showed, there was no holes, so I don't need to show them. And so now what I'm going to need to do next, I could do some fancy limit stuff, but I also can just plug in. So first, let me sketch my asymptote, right? So as a reminder, y equals x plus 3 was the asymptote. So here is 3. X plus 3, that's a slope of 1. So I'm going to try to make sure that I'm doing this to scale. This is an asymptote. It's not the graph, it's the asymptote. And again, that's the equation of the asymptote. Okay, so I know that I'm going to fill in here and here, or I might be filling in here and here. So now I need to test a value. So I'm going to choose 0 because it's always just so easy to plug 0 in. So I'm going to plug 0 into my original. This was my original. Just copying from the top of the paper. 0 squared plus 5 times 0 plus 2 over 0 plus 2. Bop, bop, bop. 2 over 2 equals 1. So that means that there is a point at 0, 1, a regular old point. So 0, 1. So since I know the dot exists there, that means that it has to be this sort of shape. And that would be plenty to get you full credit. If you really want it to be like as perfect as possible, you can plug in a bunch of other points, but this would be full credit. And going to our rubric, part 5, we had our vertical, we had our oblique, we did the synthetic division, we did a test value, and we had an accurate graph. So that is all perfect. Okay, on to the next part. Okay, part 6. It says use the limits definition of derivative. Okay, cool. So we learned about limits very recently. And of course, we have our little song. So just as a reminder, we have f of x plus h minus f of x all over h. Plug in 0 for h. And simplify, and simplify. And that's what we're going to do. So we have to have this definition memorized. We're going to see it forever. As long as calculus is in your life, you will see this definition. Okay, so we're going to go through the steps. So we're going to start with this part first. F of x plus h. Okay, so following this rule, I'm going to take my input and square it. In this case, my input is x plus h. So now I need to do a little, algebra here. And this work is going to give me x squared plus 2 hx plus h squared, and then bring the minus 2 down. Okay, so this is f of x plus h. And then we're going to subtract f of x from that. Here's f of x. Okay. So this part right here is us focusing. I'm just going to kind of highlight it with a green marker. This is equal to this right now. Okay. So we need to distribute this negative, and then we'll be able to get rid of all these brackets. So we have, I'm just copying down the first part. And now I'm copying down the second part, but with the negative distributed. So now it's +2. And as usual, we're going to see some cancellation. These two items cancel, and these two items cancel. So that means all that's left here is 2hx plus h squared. So that is the top of our fraction. And now we need to do the other part, which is to divide by h. Okay, so here I go, divide by h. Well, that's going to cancel out an h in the first term, giving me 2x. And then h squared divided by h gives me h. If it's helpful, this is a side note. This is extra. You don't have to do this. For this part, if you're like, wait a minute, I'm confused, you can factor the top if you don't want to do it the way I showed. So like an h gets pulled out, 2x plus h divided by h. You also could have thought of it that way. Either one of these is fine. Okay, so cool. There's one more step. And that one more step is that it says that we're taking the limit as h approaches 0. So now I need to plug in 0 for h. So limit h approaches 0 of 2x plus h. Well, plug in 0, you're just going to have 2x plus 0, which is 2x. So that's this answer. And then to get this answer, you need to plug in the x value. So 2 times 3 is 6. Cool. All right, that was part 6. Let's take a quick look at our rubric. Okay, so use limits definition. This has to be there. Cool. Do the math. Looks good, looks good, looks good. Cool. Find the right answer here. Find the right answer here. Cool. All right, that's part 6. Here we go on part 7, which is the biggest part of the test. Brace yourself. Just kidding, sort of. All right, here we go. All right, so we are going to use derivatives. We're going to find relative extrema, intervals of increase, decrease, points in concavity, etc. All right, so here we go. So with these types of problems, the first thing that we are going to do is find the first derivative. So using power rule, 3 times 2 is 6. 3 minus 1 is 2. Minus 2 times 3 is 6. 2 minus 1 is 1. So it's x to the 1. Minus 12. Right? 1 times 12 is 12. And then there is a 1 here. 1 minus 1 is 0. We don't need to write x to the 0. And we know the derivative of the constant is 0. So we don't need to write plus 0. So this is the first derivative. Okay. Now we know that in order to figure out where the relative extrema are, in other words, the max and min, we now need to set this equal to 0. So derivative equal to 0. I'm going to factor. I see a 6 goes into all 3 of these things. Okay, cool. 6x squared minus 6x minus 12. Okay, great. All right, so now we're just going to factor this. We have a minus 2. We do minus 2 plus 1. Let's double check. X times x is x squared. X times 1, positive 1x minus 2x does give us negative 1x. Okay, we're going to set these 3 pieces. Well, we don't really need to say 6 equals 0 because we're just going to throw that out since it's false, but we could write it if we want to. Okay, so one of them is x equals 2, and one of them is x equals negative 1. So just to keep track of my work, I'm going to look at the next page. I know that the 2 and the negative 1 go in. Oops, sorry. I know that the 2 and the negative 1 are going to go in these places, but I'm not sure yet which is a max and min, so I'm just going to come back to that. Okay. You can absolutely grab more paper at this point. Feel free to pause the video if you need to. I'm going to try my best to put it right here. So here's my number line. Here's negative 1. here's 2. I'm going to start testing some values to see if I get positive or negative numbers. So test. So a number over here would be -2. So if I plug -2 into the derivative of -2, I'll have 6 times -2 squared minus 6 times -2 minus 12. Okay, so 6 times 4 is 24 plus 12 minus 12. I can already see it's positive. Okay, so this is positive. If you instead used a calculator and just plug in -2 into the first derivative and showed that you got positive, that's fine. That counts as full work. Okay, next interval. From -1 to 2, 0 is in between there. So I'm going to test 0. So the derivative of 0 is going to give me 0 minus 0 minus 12. So that's a negative number. Negative. Okay. All right. After 2, 3. I'm going to test 3 because that's a number that's in this interval. So the derivative of 3 would give me 6 times 3 squared minus 6 times 3 minus 12. 9 times 6 is 54 minus 18 minus 12. 54 minus 30 equals a positive 24. Positive. Okay. Okay. So I'm going to pause here and I'm going to take this information over to my next page. I'm going to hold it like this so we can see where all the info is coming from. Okay. So intervals of increase. That's increase means where first derivative is positive. So that's before -1. So from -infinity to -1 and from 2 on. And it has to be a soft bracket because -1 and 2, it was equal 0, which means it was neither increasing nor decreasing. It was turning around. Decreasing was where the first derivative was negative, and that was from -1 to 2. Okay, I'm going to draw a line here because we'll come back. So we have this so far. Now here, we want to envision this. So when a graph is increasing and then decreasing, it'll look something like this. That would be a maximum, max. So max is happening at -1. I don't have the y value yet though. When something is decreasing and then increasing, that's a min. So we know that the min is at 2. Take a sec to process this. Okay. Now we want to get these numbers. In order to get them, we need to plug these numbers into the original. So here we go. As a reminder, the original graph was this. I'm just going to copy it. And if you need more paper, that is totally fine. Okay, so we're going to plug these numbers in. You can use a calculator. You do not need to do it by hand, but you also can do it by hand. So -2 minus 3 plus 12 plus 20, 32 minus 2, 30 minus 3 is 27. Okay, so relative maximum is happening at 27. All right. Now let's see what the original for 2 was. 2 times 2 cubed minus 3 times 2 squared minus 12 times 2 plus 20. 8 times 2 is 16 minus 4 times 3 is 12 minus 24 plus 20. All right, so 16 minus 12 is 4, minus 24 is -28, plus 20 equals -8. So relative max at -1, 27, relative min at 2, -8. Okay, now it says to talk about concavity. The way we do concavity is second derivative. So as a reminder, just copying from the page before, the first derivative was 6x squared minus 6x minus 12. Therefore, the second derivative is going to be 2 times 6 is 12, x minus 6. And again, the exponents went down by 1. Derivative of the constant is 0, so we don't write it. I need to know when this is 0. Okay, so I know the point of concavity is at half comma something. I'm going to draw my little number line. And I'm going to test a value before half. So I'm going to test 0. So the second derivative of 0 gives me -6. So that's negative. And the second derivative of, let's test 1, gives me 12 times 1 is 12, minus 6 is positive 6. So positive. Okay, so this was the second derivative, which tells us about concavity. Concave down is before half. Concave down when the second derivative is negative. Concave up when the second derivative is positive. Okay. All right, now I need to know this. So I need to now go to my original function and plug it in. So original f of half equals, going to be 2 times half cubed minus 3 times half squared minus 12 times half plus 20. You can absolutely do this in the calculator and then write the answer and then just put a note that use the calculator. You do not need to do what I'm doing. 1/8 times 2 is 2/8, so that's 1/4 minus 3/4 minus 6 plus 20. Okay. Okay, well, let's see. This is -1/2. Yep. And this is 14. So 13.5, 13.5, 27/2. Those are all perfectly fine answers. That's your point of concavity. Okay, feel free to pause the video if you need to. The final thing that we're going to do is on part 7 continued. It says to sketch it. It says to label relative maximum, relative minimum, and point of inflection. Okay, here we go. We have all this information right here. Okay, the biggest, highest y value I see between these 3 points is 27, and the lowest one I see is -8. So when I go to scale my graph, I'm just going to put 27 up top, and then that's 18, that's 9, and then I'll put -8 here. It doesn't need to be perfectly scaled, but try to make it like, you know, somewhat accurate. Okay. 13.5 is half of 27, which worked out nicely for me. So I'm just going to mark the 13.5. Okay. Looking at the x values, the lowest x value I see out of these 3 points is -1, and the highest is 2. So I'm going to put -1 here, and then I'm going to try to scale it 1, 2, and I know I'm going to need the half, so I'm going to mark it. Okay, so here we go. I'm going to mark my half 13.5. I'm going to mark my -127. And I'm going to mark my 2 -8. And I know that this was a max. Oh, and I also, this is not like mandatory, but you also know the y-intercept is 20. So that's helpful for when you're trying to graph, because the original had a y-intercept of 20. So I'm going to go like here-ish. I know that's a point on my graph. Okay, so I'm going to gently start to connect these points. And I probably should have done pencil, but that's all right. I know this is a point of inflection, so this is where it should start to kind of shift a little bit. I know this is a min, so it has to turn around. I know this is a max, so that's why I knew I had to turn around. I need arrows, and I know this is a point of inflection or a point of concavity, and I want to label them with their values. And I'm going to put R for relative max, because the real max is over here. It's infinity, but relative max. And then relative min, and that was to -8. Cool. Okay, that is the test. Let's just use our rubric really quick to make sure that we get our 20 points for part 7. Okay, so to review what you just did in part 7, it started back on page 4. Okay, so correct derivative of f, Find the zeros for the derivative of f. We did the work here to find the 2 zeros. Choose and test 3 appropriate intervals. We tested 3 intervals and we found the results. Correct intervals of increase and decrease. We looked at these numbers. And using those numbers, we filled in this right here. And again, we did that by using this information. Find relative max and min. We figured out if there was a max or min based on this information. Put it here. Then plugged these x values into the original to get these numbers. Correct max and min. Then found the correct second derivative. Find the 0 for the second derivative. Test 2 intervals. We did that here. Correct intervals of concavity. That's here and here. We knew when it was concave up and concave down. Correct point of inflection. We knew it was at half. We plugged half in to get the y value. This is how you were graded. Congratulations.